Welcome to the seminar. Today I'm going to introduce transfer learning. So today I'm going to use two examples to illustrate how to do the transfer learning. So let's start with a quick review of the basic concept of deep learning, neural networks, and the transfer learning. The code that I use in this seminar will be made available to you. You can download from this link. So a neural network is made of multiple layers, and each layer has 0 or more parameters or variables. In deep learning community, people usually interchangeably use the term like variables, parameters, or weights. But in TensorFlow, trainable variable and trainable parameters are two different concepts. So for example, in a dense layer, there are two trainable variables. One is weight, the other is bias. The weight itself is a matrix which contains multiple trainable or tunable parameters. So it's just some kind of terminology or jargon thing. So basically, they are quite similar. So once you have the neural network built up, I mean the architecture, the weights, the trainable variables are initialized randomly. So you have to train the model with data. And training itself is a process in which the trainable variables are altered gradually or iteratively to minimize a predefined loss function. So once it is well trained, you can put it in production. So so that's the general procedure to do deep learning. Probably some of you know that grafting is a very useful and a very commonly used technique in orchard. By grafting, you actually take advantage of the well-grown wood stock, so to boost the fruit production. So similar idea in deep learning. You don't have to start from scratch. So basically, you can apply the knowledge that you learned in previous applications to solve a new similar problem. So this is the basic idea, okay? The knowledge that I referred here is in the form of neural network models. So here I show, for example, a classification neural network which classify 1,000 classes. And suppose this is well trained and it is very successful, and we can use it as a root stock, or in our term, base model, okay? What we do is we cut off the top layer, and then we add new layers or new classifier to classify our new problem. For example, a 10 class classification problem. Let's assume that for example, classify the breeds of dogs or something similar, okay? The classifier itself is one or more layers, okay? So this is this concept. Then you can train the newly added layer to get the job done. So first thing in transfer learning is consider how to choose models. I mean those pre-trained models. So it's all depends on the task you are going to work on. If you are gonna create a neural network to classify images, then you need to choose a model that is image-based. And secondly, how to use the base model. You can use it as a feature extractor, which means it only provides features. And then you feed those features into the newly added layers. During training, the base model will not be updated. You only train the added layers. If this cannot achieve the performance you expected, then you will need to consider fine-tune the model. By fine-tune, I mean you unfreeze the base model. So that means you train the base model with your added layer altogether. So I will show it later on. So why we need to do transfer learning? What's the benefit? First of all, you can see that the successfully trained model is the result of many trial and errors effort by AI experts. So it is full of knowledge, useful knowledge. It's very juicy actually, partly because such a model quite often trained with large data. So that means it drew a lot of juice from those data, and form a knowledge, and those knowledge is held within the model. To hold those knowledges, and it requires the base model or the pre-trained model to be large enough, or it has the adequate capacity. So no surprise, you will see most of the base model that we are going to use for transfer learning has easily a few hundreds of layers and over millions of training parameters. So it's quite big. So otherwise, if the architecture itself is not large enough, it cannot hold the knowledge learned from a large data set. Okay. And secondly, with the transfer learning, in most cases, you only need to train the newly added layers. It's much simpler, and the training process is more easily to converge, and is converge. And I mean the convergence is faster. And another reason is sometimes you do not have a large training data, and transfer learning can handle that case better than from scratch, because most of the knowledge already learned from all kept in the base model. You can create your own train your own model previously if you think it's very successful, and later on you have a new application, I mean new problem to solve. if they are the same type, if they are text-based, or if they are all, if they both are, voice-based, you can you use your own model. And Keras also provide, a bunch of models. So I will demonstrate that as well. Lastly is the Tensorflow Hub. So Tensorflow Hub is a repository and that holds a lot of very successful pre-trained models for user to use. The precursor of TensorFlow Hub is called Model Zoo. I think probably some of you are aware of that. So so here is the link to the hub, and I will show how to choose a model for our task later on. And lastly, just a recap. So the process of transfer learning is first choose appropriate pre-trained model, and when you add extra layers at mostly at the output end. You need to make sure the compatibility. I mean, in terms of either in terms both the shape and the data type. Otherwise, if they do not match, error will occur. And secondly, never do the fine tune first. You need to first train the whole network with the base model frozen, and otherwise, because there's a large, gradients calculated from because the ideal layer has a randomized weight. So the gradient are quite large that will destroy the base model or make the base model quickly forget its own weight. So that's not good. That's not the purpose of transfer learning. Okay, so today I'm gonna show an example to classify images of dogs and cats, and using MobileNet v2 as a base model. So I'm gonna show how to load it through Keras interface, and also through another, the second one example shows how to get the base model through the TensorFlow Hub interface. So that's it. So now I'm gonna quickly show the TensorFlow Hub. So here you can see it's first based on the domain, either text or image based, or video based, or audio based. And on the each, you can see there's some is the base model is for classification, or are you gonna use as a feature extraction, or object detection, or segmentation? So in this example, I'm gonna use a feature, use it as a feature vector. So for example, if you click on this one, it shows a lot of image-based neural network with the top layer removed, so it's provide features. And on the left-hand side, you can narrow down the search by, for example, I click either I say I want a tunable, fine-tunable. And secondly, I want the architecture. For example, in this, I already have a idea. I'm going to use the MobileNet v2. You click on this one, and there's a different version of this model. Some of them are trained with different so-called depth multiplier or different input size. So I'm going to use this one. So you click on this one, and it will give you the link, which is this URL. that you can use later on, or you can download the model itself. And as I mentioned earlier, you need to pay attention to the connection. You have to make the input shape. Here is a width and height are both 224, and it's a color image RGB 3. So you need this knowledge. All right, so let's start the GitHub. So I already start the GitHub. Let me close this one. So basically, when you start GitHub on Graham, you can see that here on the left-hand side, you can see the browse the files. And the second one, I think this is the software, right? Software, okay. So here I need to load, first of all, let me open the my first example. You can see the kernel already use my default, my customized default kernel. I give it a name. 2022 ML kernel, and the example that I give in the link, you know, you can repeat. You can see how to do that. So here I'm gonna, you know, first load the required. Oh, I don't know why this shouldn't change. Okay, I select. Let's turn back. So first I need to load module load SciPy stack. So here I'm gonna load this one. Okay, and then I need load a CUDA because I'm using GPU. I'm gonna use this version. Okay. CUDA as well. Okay, I think I'm ready. Okay, so this is my first example. In this notebook, I'm going to do 5 steps. So first, I'm gonna load the so let's run this one because sometimes the import module takes some time. So I let it go. So there, I'm going to do the task in 5 steps. First, I'm going to load the pre-trained model, which is mobile net 2 v2. So we are going to inspect the model to get familiar with it, and then I'm going to add new layers. And after that, the network is ready. In step 3, I'm gonna load and examine the training data. After that, I'm gonna, you know, train the model with the data. And lastly, I'm gonna fine tune it. So that's the process. Okay, so I already import those required Python modules like NumPy, TensorFlow, etc. So the second cell that I'm gonna run is I define the size of the model. For this model, I would say that the input size could be 224 by 224, or another is it's 116 by 160. Oh, 160 by 160. Okay. But the minimum size is 32 by 32. Couldn't be smaller than that. So this is. So I'm gonna use this image size, and the shape of the image I just add 3. It's RGB. So let's load it, run it. So basically, I think it's done. Okay, it's finished. So there is some message printed out about the GPU and the memory thing, so don't need to worry about it. So now after that, we already loaded, we loaded the base model with this through the Keras interface. And in the interface, I said, okay, I want the one that without the top layer, or like I said, I removed the top layer already. And I want the base model trained with the ImageNet data sets, which is quite a large data set, okay? So now, because this is loaded, let's take a summary to see the structure. You can see that the input shape is 160 by 160 by 3. And then it goes through a convolution layer, and the shape changes to 80 by 80 by 32, and so on and so forth. You just quickly skip the middle layers. You don't need to worry about it. You need to pay attention to the end. Okay, in the end, the output shape from this base model is 5 by 5 by 1280. So remember this. And also, it shows that it has more than 2 million parameters, but none of them is trainable. This is because, let's quickly go back. I set the trainability to false. I think it's somewhere here. Yeah. All right. So let's go back. Now I'm gonna further to check something like how many layers in this model. Let's run it. It's 154. And then we check the last layer in this way. It's just to reconfirm that the after shape is 5 by 5 by 1280. Okay. And after that, we are gonna add some layers at the output end. So because the shape from the base model is 5 by 5 by 12, we first want to get to convert it to a flattened vector, the size of 1280. So we use global average polling. So we use this one. So convert this shape to this shape. After that, we got a feature vector of length 1280. Then we use a dense layer to just output one. Why one? Because here we only need to distinguish either a dog or a cat. So it's a binary classification. We use only one to indicate that. So after that, we created these two layers. Okay, just remember. At the input end, usually it's some of the options is optional, but for example, we want to do some data augmentation by random flip, horizontally, and by slightly rotation of the image, so to increase the training samples or increase the variety of the training samples. All right, so we defined these two layers. And another thing that I need to mention that is the input, although the size is as I mentioned, is 160 by 160 by 3, but the input image data value we loaded from the image is in the range of from 0 to 255. we need to remap it into the range of -1 and 1. So we scale it halfway and shift it by -1. So we call this layer rescale. So now we have everything ready. Let's put it all together. So we first create an input layer, and we specify the shape is 160, 160, and 3. And we first let the input go through the data augmentation layers or modules, because it contains 2 layers. And after that, we rescale it. And after that, we pump or we feed the altered input data into the base model, and we mark the base model as training. We say we set it false, so we are not going to change the. Basically, we freeze the base model, and after that, we do the global average, like I mentioned above, this one. And finally, I add something like a drop-off layer. This is used to a kind of reduce the effect of overfitting. From this drop-out, the output from this layer, I feed it into prediction layer that I define above, which is just a dense layer. Okay. All right. So now we create a model that encapsulates all the way from the beginning, from the input to the output. Okay. The model we just call it model. Okay. Now let's check the data. The URL is here, and I use the Keras interface to get the data, get the directory. One thing that I need to mention that because the compute nodes on Graham do not have internet access, so you have to pre-download it. You need basically on the login node, you need to do it on the I already done it. So the data is already in my home directory, in the subfolder called keras.dataset or dataset or something. Okay, it's there. So now I'm gonna, create this for this directory path, and we define a batch size 32, so that a batch contains 32 samples. So we then, form the training data set. We all use Keras interface to do that. So this is just a simple, function call, and do the same thing to get our validation data set. So there's no test data, but we later on we split the validation set. Split a little bit as a test set. So just quickly check if this is correct. First, we got the names of the class, dog and cats. And now I'm gonna plot the first batch, because the first batch contains 32 samples. We only plot, I think 3 by 3. Okay, we only plot, 9 of them, the first 9 of the 32. Oh, sorry. Did I run it or no? Let's run it. Okay, sorry. I haven't run a lot. Okay, from here, let's run this one. I created the layers that are going to attach to the outputs end. Create a layer that I'm going to attach to the beginning. Create the model. Load the data. Run it again. Let's examine the data. So I'm gonna plot a 3 by 3. Take some time, or let me see. Yeah. So here you can see that I just show some examples to make sure the data loading is correct. I can see, okay, the first image is a dog and it is labeled as dogs. So that's correct. The second one is a cat, it is labeled as cats. So on and so forth. I just quickly go through. Okay, everything looks good to me. So next, I'm gonna, like I said, I'm gonna split the registration side. I'm gonna split 1/5 as a test date set. So do that. So now I have 26 batches of validation set and 6 test batches. Next, I'm gonna make a prefetch, enable auto prefetch. So this is a good feature of TensorFlow. So this feature enables when the CPU is busy doing training, and it can prefetch the batch data for the next round, for the next iteration. Okay. Now, almost ready. So this is not necessary because I already make the trainable false. Now I'm gonna compile the model. I use this as a not very large as a learning rate, and this is my loss function, which is binary cross entropy, and just do it. Let's see a summary. So this time, the model that we create, you can see we add something on the top. First is the input layer, and then there's a, I think this one is the so-called sequential. Is a combination of 2 layers for the flipping, random flipping, and rotation. And after that is scaling. Okay, scaling the range from 0 to 255 to between, and map it to -1 and 1. Okay, so after that is the base model, which contains a lot of more than 2 million parameters. After that, we got global polling, which is what we add, and drop out, and the dance. So you can see that pooling and drop out do not have parameters, and only the dance has 1281. Why 1281? Like I mentioned earlier, it takes the input of the dense layer is 1280, and so each the output is 1. So each connection has a weight associated with it. So that is 1280 weights, and the 1 is the BIOS. So you need to understand this. So after that, let's keep going. Oh, where is it? Okay, sorry. Okay. Okay, here. So here is another example that although we have 1280 trainable parameters, but the trainable variables only 2. Like I mentioned earlier, it's weight matrix and BIOS. Now let's train the model 10 epochs. So you need to pay attention to the loss and the accuracy. which is the first after first iteration, it's 58%. So you should know that a binary classification, if you do random guess, you can get 50% correct. So it must be greater than 50. So you can see 80, okay, 80, 84. Finally, I got something 91% on the training data, and 96% on the validation data. Sometimes you wonder why this happened, why the accuracy on the validation data is higher than the training data. It's you know, it's just against our intuition. The explanation is like this. One thing is because when you do the accuracy calculation for the training data, all the like the batch normalization layer and the dropout take effects, so that will affect the accuracy. And now let's plot it. You can see this is the plot. The first one is accuracy, the other one is loss. You can see, yeah. Although you know, you get like 96% accurate on the validation set, which is pretty good. You can do even better job if we do fine-tuning. So now at this point, let's do this. So first you make the trainable, make it true, run it, and then you print out the layers. We already know it's 154 in previously. So I unfreeze the whole model. After that, I freeze the layer from the input layer all the way to 100th layers. So that means that the remaining 54 layers are unfrozen. So that means we only train the top 54 layers with our added layers. So let's do that. So once we readjust the trainability, we are gonna compile this model again to make the change take effect. And the summary again, I just quickly go, oh, sorry. So here you can see that previously the trainable parameters is 1281, but now it's 1.8 million. Most of them come from the 54 layers of the base model. Okay. Run the trainable parameters, trainable variables. You can see that it's 56. So the last layer dense count 2 variables, and the remaining 54 each has 1 training variable. So this is another example that TensorFlow has different definition for trainable parameters and trainable variables. So it's a kind of odd to some beginners to TensorFlow. Okay. So now I'm gonna train it. Still train another 10 epoch. So just like this, fit. Yeah, I think that's it. So let's do it. It will continue the training. Yeah, you can see. Yeah, so basically we got 2% improvement over the accuracy, classification accuracy. So next I'm gonna do the same thing, plot the curve, and you can have a look. And lastly, it's not so necessary, but I'm gonna evaluate the model that I already trained so far, fine-tuned so far. I check the loss and accuracy. So on the test data, which is 1/5 of the original validation data set. So I got 98.4%. So it's pretty good. And let's do, sorry, what's that? Lastly, I ran the model on the test data, on the test data set, the first batch of test data set, and print out the result, which the first row is the prediction. The second row is the ground truth, the true labels, and you can each of the vectors contains 32. It's because our batch size is 32, and you quickly check the two rows. You see they are identical, and I also print out the first 9 and label them with our prediction. You see, label them with our prediction, and to see if they're correct. Just visually check. You can see the first one is cat, and it's labeled cat. The second one is dog, labels dogs. So looks good. So this is our, wow, something wrong, but never mind. So this is our first example. The next example should be easy. Let's go back. I'm gonna close this one. Discard, I don't want it. I probably need, I think I see that error. Sometimes I need to restart the kernel. Give us a restart kernel, something wrong. All right, so this is the second example, which is quite similar to the first one. And the difference is we are gonna load the base model through the Tensorflow Hub interface. And so I just quickly go through the steps because most of them are identical to the previous one. The first one is the same. And the second one, you can see that I use image size 224. Like I said, it could be the minimum is 32 by 32. Okay, you need to pay attention to this statement. Okay, this one is the how we create, we get the base model through the TensorFlow Hub interface. You can see it called a Hub Keras layer. So basically, the whole model after this one is it return a special layer. I think right now with this the current version of Hub API, we do not have the flexibility to for example to change the trainability of each layer within the base model. We can either turn them on, let's say we fine-tune everything in the base model, or we freeze it. So there's no, at least I cannot find any other way to selectively change the trainability within the model. So here I first create the use use this interface, And this link is actually comes from here. Oh yeah, from here. Copy, if you check just this link. Let's go back. So I copy paste the link here, and this is the model. I make it a trainability, turn it off or false. After that, I'm gonna, create a sequential, because this base model is just a layer. You put it here. After that, I have a dropout, a dance. You wonder why you don't do the global average pooling here. It all depends on the shape. I will show you probably okay, probably here. Like I said, when you do transfer learning, you must pay attention to the shape. Okay, so you see this part, the output of the model is a feature vector, has a size 1280. It's no longer 5 by 5 by 1280. So that means, although we seems to load the same model called mobile net v2, actually they are slightly different. You can find something. I don't know why the implementation caused, but it's slightly different. Also, here this base model accept the image with the date range from 0 to 255. That's another different. So okay, so I'm creating this. So let me run this. So I run this one. Okay, run this one again. Okay. Oh, one more thing that I need to mention, like kernel project appear to be have that. It will sit down. Okay, I don't know what's going on here. So let's try again to see. First, I need to make the kernel. This one. Yeah, sometimes Jinhui is an expert at Jupyter Hub. I'm a new beginner. Let's run it again. Okay, looks good. Keep going. Okay, this looks good. So the model, base model is loaded as a Keras layer, and keep going. I think it's done, right? Yeah. And then create the model and do the summary. I can see that most parameters in the base model, that's correct. And yeah, exactly. So far we only have 1281 trainable parameters. Let's keep doing and load our data. The same thing as before. Go. Give it a little bit time. It's not finished yet. Okay, now it's just like I previously showed those things. Keep doing and make them prefetchable and turn off the base model and compile the whole thing. Now pay attention to that. When I first do the the learning with the base model frozen, I use the learning curve, which is just like this, 0.0001. And then let's keep going. So the two trainable variables like before. Now I'm gonna train it. You can see that without date augmentation, and also because the output shape is different from the one with that loaded with Keras interface. Because here we only have 1280 features, so you can see that the accuracy is not so great. So for the validation, we got 62. So that is too low. So we are gonna keep we are going to do the fine tuning. So first of all, draw the curve. You see, it doesn't look good at all. And now I'm gonna unfreeze the base model to make the trainable true. And I'm gonna compile it. And this time, you can see that I make the trainable, make the learning rate 10 times smaller, okay? And do the summary again. Summary again. Yeah. So now you can see the trainable parameter is 2 million something. So that means you include the base model. Okay. And what is it? Oh, sorry. So the trainable variables, parameter variables, I just show the difference. And let's do the fine tuning. Also 10 epochs fine tuning. Let's see, we got some, if we can get slightly better result. Yeah, looks good. The accuracy on the validation after first epoch in the fine tuning, we got like 83, so it's pretty good. I would like to take the moment to mention another thing. Batch normalization is a very special layer. So you do not wish to tune it because it can ruin the model. If you do, I think you should keep the momentum, I think, big enough so that it won't influence too much by the new training data. So that's another thing I need to mention. Yeah, almost all slightly better. Yeah. So let's plot the accuracy. You can see. Okay, so this is the curve. So before and after fine tuning, you can see the curve. So pretty good. Okay, let me see. Oh yeah, I did that. So finally, evaluation on the test set. So we got close to 99. Yeah. So also plot the yeah. So the same steps as previous examples. So we got yeah. We can take a quick look. So that's pretty much it. And I do not have fruit material to mention, so it's time to answer questions.